Finally, we're ready to define curvature. Let's begin by recalling some examples from the previous lectures. This is the Euclidean plane. This is a sphere. These are both two-dimensional spaces, and they're drawn in these pictures as surfaces in three-dimensional space. These two-dimensional spaces are, of course, very different. The Euclidean plane is flat, whereas the sphere is curved. Now remember, there are two types of geometries, or two types of curvature that we can talk about. There's intrinsic curvature, the intrinsic curvature of a space or a space-time just depends on the intrinsic properties of the space itself. On the other hand, extrinsic curvature depends on the way the space is embedded in a higher dimensional space or space-time. Higher dimensional space or space-time. So the sphere, for example, is both intrinsically and extrinsically curved. The Euclidean plane, as it's been drawn here, is both intrinsically and extrinsically flat. But we could, if we wanted to, take this, if this is, say, a piece of paper, we could take this piece of paper and put a little bump in it. And now the piece of paper is still intrinsically flat. Its intrinsic properties have not changed, but extrinsically it's now curved. Notice that these two spaces are both the Euclidean plane. We've just changed the way that this two-dimensional surface is embedded in the higher dimensional space. So how do we define curvature mathematically? Let's start with extrinsic curvature. So once again, this is the sphere, and it's embedded in three-dimensional space. So we pick a point on the sphere, say a point P right here, and we construct the normal vector to the sphere. So this is the unit normal. It's a unit vector as defined in the embedding space, three-dimensional space. And now we parallel transport that vector to another point, say point Q. And this is the normal vector that sits at point Q. And when we parallel transport this vector, we parallel transport it as a vector within the three-dimensional embedding space. So the parallel transported vector would look like this. Then we subtract these two vectors, and that gives us a quantitative definition of the extrinsic curvature of this space. And now intrinsic curvature. So here's a sphere. Now let's choose a vector at some point. Let's say this point right here. And let's choose the following vector. So this is actually the vector minus d by d theta at the point theta equals pi over 2, so it's at the equator, and phi equals, well, I don't know what phi is, but it doesn't matter. Notice I've drawn this vector as if it's sitting in the embedding space outside of the sphere, but really it's defined intrinsically, just in terms of the intrinsic geometry of the sphere as minus d by d theta. So it's only drawn this way to just make it clear where the vector is. The vector, again, it lies in the sphere, or the mathematicians would say the vector actually lies in the tangent space to the sphere. But the point is it's defined intrinsically. Its definition has nothing to do with the exterior three-dimensional space in which this sphere is pictured as being embedded. So now what we're going to do is take this vector and parallel transport it around a loop, and when we bring it back to where it began, we'll see if the vector has rotated or changed any. So we'll take the loop to be along the equator to the far end, then across over the North Pole and back. So keeping this vector always parallel to itself, we bring it around the equator to the far end, then up to the North Pole, and then back down to where it began. So this is the beginning vector, and this is the ending vector. Of course, they're very different. We can subtract them and see what the change is. In this example, the vector is rotated by a full 180 degrees. And the amount of change in the vector when we bring it back to the original point is a measure of the amount of curvature inside the loop. Of course, we could carry out this same analysis for the Euclidean plane. Here's the Euclidean plane. Here's a loop. So we take a vector and parallel transport it around the loop. And when we return to the original point, we'll find that the ending vector coincides with the beginning vector. And that's just telling us that the space in the neighborhood of this loop is flat. Now let's turn our attention to four-dimensional space-time. Currently, there's no experimental evidence that our four-dimensional space-time is embedded in any higher dimensional space-time. So the only type of geometry or curvature that we can consider is the intrinsic geometry. So our goal will be, given a space-time metric, g mu nu, to compute the change in a vector. Let's call the vector u, as it's parallel transported around a closed loop. And I should emphasize at this point that the concept of curvature is a local concept defined at each point in the space-time, and it can vary from point to point. So the closed loops we consider, we will want to take them to be infinitesimal. So each infinitesimal closed loop will characterize the curvature at the point where that infinitesimal loop is located. So let's define our infinitesimal loop as x mu of lambda. So lambda is an arbitrary parameter along this world line, and the world line is closed. So let's draw it like this. Let's start with some point P, and now here's the loop. It's given by x mu of lambda. And since it's closed, let's let lambda range from, say, 0 to 2 pi. Doesn't really matter, but let's just use 2 pi. So this point P is the point x mu of lambda equals 0, and it's also the point x mu of 2 pi. And now we're going to take a vector starting at point P, vector u, and parallel transport it around this loop back to the point P. Now when we parallel transport this vector u around the loop, we create a vector field, a vector at each point on the loop that has the property that its covariant derivative along the loop vanishes. So parallel transport tells us that the covariant derivative along the loop, so this is the tangent vector to the loop, x dot, covariant derivative of u is equal to 0. Now if we write this out in more detail, this is x alpha dot, and remember the dot is d by d lambda, times partial alpha u mu plus gamma alpha mu beta u beta equals 0. And using the chain rule here, we find this is u mu dot plus gamma mu alpha beta x dot alpha u beta equals 0. So let's make sure the meaning of this equation is clear. The dot is d by d lambda. So here's our point P, here's our loop x mu of lambda, and we've taken a vector at the point P and parallel transported it all around the loop to create a vector whose components are u mu, and the components depend on the point you are on the loop, so it depends on lambda. Right, so this equation is actually, in more detail, this is the derivative with respect to lambda of u mu of lambda plus gamma mu alpha beta, and the Christoffel symbols are evaluated along the loop. So these are functions of the space-time coordinates, which are in turn functions of lambda. Then x dot is partial x with respect to lambda, and u is function of lambda. Now let's bring this term to the right-hand side and write this result as partial with respect to lambda of u mu of lambda equals minus gamma mu alpha beta, which is a function of x of lambda, times partial x alpha with respect to lambda times u beta of lambda. And now let's integrate both sides from 0 to 2 pi. On the left-hand side, we have the integral of the total derivative, so that's just u, the components of u at 2 pi, minus the components of u at lambda equals 0. And we should be careful here because the vector field u is actually discontinuous at this point P. That point P is the point where lambda is equal to 0. It's also the point where lambda is equal to 2 pi. But what we can do is we can integrate from a value of lambda that's slightly larger than 0 to a value of lambda that's slightly smaller than 2 pi, and then take the limit. And then what this will be is the starting u, or the beginning vector, and this is the ending vector. So this is just the quantity we want to compute. We want to compute how much the vector changes as it's parallel transported around this complete loop, and that change is just given by this difference. Let's go ahead and call this change in u delta u. And then that equals minus the integral from 0 to 2 pi of d lambda times Christoffel symbols gamma mu alpha beta evaluated along the loop x of lambda times, we'll just call this x dot alpha of lambda, and u beta of lambda. Let me draw a picture of the loop one more time. So this is our point P, which is given coordinates x mu of 0. That's the same as x mu at lambda equal to 2 pi. And we'll just denote that x mu sub 0 for shorthand. All right, now here's a point lambda, a generic point along the loop. This has coordinates x mu of lambda. And what I want to do is to find now a displacement vector. So let's define the displacement vector which we'll call v mu. So v mu, and it depends on lambda, is just x mu of lambda minus x mu 0. Okay, and now v is going to be small because this loop is infinitesimal. And so we can now write our coordinates of the point lambda along the loop as x mu naught plus this displacement vector v. And of course, if we differentiate this with respect to lambda, we have x dot is equal to v dot. So now we can use these to rewrite our result for the change in u in the following way. We have delta u mu equals minus the integral from 0 to 2 pi of d lambda times gamma mu alpha beta, which is a function of x of lambda, but we can now write that as x naught plus v. V, of course, depends on lambda. Then we had x dot alpha, but that can be written as v dot alpha, and then times u beta of lambda. Now, since v is small, we can expand the Christoffel symbols in a Taylor series. So this equals minus integral from 0 to 2 pi d lambda of gamma mu alpha beta at x naught. That's the leading order term in the expansion. The next term is partial sigma of gamma mu alpha beta evaluated at x naught times v sigma of lambda. And then there are higher order terms that we'll ignore since we're letting the loop be infinitesimal, which means v is small. Then times v dot alpha u beta. Now let's write these terms separately. The first term is minus, now notice the Christoffel symbols here are evaluated at x naught. This doesn't depend on lambda, so we can pull that out from the integral. And it's evaluated at x naught. That's the point P. If you'll recall from the diagram, x naught is just the point P. So I'll put a little symbol here that it's being evaluated at point P. That's times the integral from 0 to 2 pi of v dot alpha, which depends on lambda, and u beta, which depends on lambda. So that's the first term here. Now the second term, again, the derivatives of the Christoffel symbols are evaluated at point P, so we can bring that out from the integral and remind ourselves that that's evaluated at point P times the integral from 0 to 2 pi of v sigma v dot alpha times u beta. Now in this first integral, let's carry out an integration by parts. So this we can write as integral from 0 to 2 pi of d lambda times derivative with respect to lambda of v alpha u beta minus the integral from 0 to 2 pi d lambda of v alpha u dot beta. Now this first term is just v alpha u beta evaluated at 0 and 2 pi. But remember, v alpha, it's a function of lambda, and is defined as x alpha of lambda minus x alpha naught, or x alpha at lambda equals 0. So that means v at 0 and v at 2 pi both vanish. So this first term just gives 0. And for the second term, we have minus integral from 0 to 2 pi d lambda v alpha. And for u dot, remember u is defined by parallel transport around the loop. So u beta dot satisfies u beta dot plus gamma beta sigma rho times x dot sigma times u rho equals 0. So we can use this to replace u beta dot with minus gamma beta sigma rho times x dot sigma u rho. And now we see that this integral is equal to minus and minus gives plus, the integral from 0 to 2 pi of d lambda times v alpha, and we have a factor of gamma, beta, sigma, rho, and that's evaluated at x of lambda. And we have a factor of x dot sigma, but remember x dot is just v dot, just differentiating this definition. So this is v dot sigma times u rho. Now the Christoffel symbols are evaluated along the loop at x of lambda, and x of lambda, remember, is x naught plus v of lambda. And we can expand this in a series since v is small, and the leading order term is just gamma evaluated at the base point p, then plus the higher order terms in v. So remember, v is small, and we already have two factors of v in this expression. So these unwritten terms would contribute third order terms in v, but we're doing this calculation to just second order in small quantities. So we can drop these terms and just evaluate the Christoffel symbols here at point p. So this integral then becomes gamma, beta, sigma rho evaluated at point p times the integral from 0 to 2 pi of d lambda times v alpha, v dot sigma, u rho. We can now put all of this together. This integral is what we obtain by simplifying this integral right here, and this whole expression is the change in the muth component of the vector u as it's parallel transported around the loop. So inserting that integral into here, what we have is delta u mu equals minus gamma mu alpha beta evaluated at point p times this integral, so that's gamma beta sigma rho at point p times the integral from 0 to 2 pi of d lambda v alpha v dot sigma u rho. And then we also had the term minus partial sigma gamma mu alpha beta evaluated at point p times the integral from 0 to 2 pi of d lambda times v sigma v dot alpha u beta. Now notice both of these terms have a factor of the integral of d lambda v dot u, but the indices are scrambled between these two terms. So I'm going to replace some repeated indices. So first of all, let's replace beta here with nu, and I'm going to replace alpha with beta. And here I will replace sigma with alpha. And I'll do the same thing for these terms. I'm going to replace rho with nu. So this rho becomes nu. We'll replace sigma with beta. And now notice I have a repeated index beta here, so I better call it something other than beta. Let's, well, since we are not using sigma anymore, let's go ahead and use sigma here. And then finally, this alpha can just stay as it is, as an alpha. And now these two terms both have the same integral factor. And we can factor that out so that the change in u can now be written as minus partial, this term first, partial alpha gamma mu beta nu minus gamma mu alpha sigma gamma sigma beta nu, all of that evaluated at point p, times the integral from 0 to 2 pi of d lambda times v alpha v dot beta times u nu. Now let's examine this integral factor a little more closely. This is the integral from 0 to 2 pi of d lambda, and both v and u are vectors that depend on lambda. So this is v alpha of lambda, v dot beta of lambda, and u nu of lambda. But the vector u, which is being parallel transported around this infinitesimal loop, it doesn't change very much as we transport it around the loop. In fact, we can see that already in this expression that shows that the total change in u from the beginning of the loop to the end of the loop is proportional to 2 factors of v, 2 factors of this small quantity v. So to leading order, we can just evaluate this vector u at the base point p, and we can write this as u nu at point p times the integral from 0 to 2 pi of v alpha v dot beta. Then our expression for the change in the vector u can be written as minus partial alpha gamma mu beta nu plus gamma mu alpha sigma gamma sigma beta nu. That's multiplied by u nu, and everything here is evaluated at point P, and then multiplied by the integral from 0 to 2 pi of d lambda v alpha v dot beta. So what is this mysterious integral factor? Well, let's draw the picture once again of the loop. Here's the base point, P. This is the loop parameterized by lambda. Here's some generic point, lambda, along the loop. So what I'm drawing now is the displacement vector. This would be the vector with components v alpha of lambda, and a nearby point with parameter value lambda plus d lambda has the displacement vector v alpha of lambda plus d lambda. Now, of course, the difference between these two vectors, v alpha of lambda plus d lambda minus v alpha of lambda, if we divide that by d lambda and take the limit, that's just what we're calling v dot at lambda. Right, so the difference, I'll draw in red here, this is the vector v alpha dot of lambda times d lambda. And notice all of these displacement vectors are vectors at point P, and really this vector v dot, it's defined as the difference between two vectors at point P. So this is also a vector at point P, even though I've drawn it like we do in elementary physics from tip to tip of these arrows. It's really a vector at point P. So these are all vectors at point P. And in fact, in the integral here, we're just combining vectors at point P and summing them in the sense of taking the integral over all of those vectors. So what we have in the box here is a combination of vectors at point P. So we can see from the free indices that these are the components of a tensor at point P. So we'll call that tensor A. So A alpha beta is integral from 0 to 2 pi over d lambda v alpha v dot beta. This is a tensor of type 2, 0 at point P. And because this tensor A is constructed from vectors that span the loop, A defines the plane of the loop. So, for example, let's assume that our loop lies in the x1, x2 coordinate plane. So what I mean by that is, remember, the loop is defined by x mu of lambda, this world line, and so I'm assuming here that x0 of lambda and x3 of lambda are 0 along the loop. Okay, so now let's take our tensor A and expand it in a coordinate basis. So this is A alpha beta, the components, times d by dx alpha, outer product with d by dx beta. But since the loop lies in the 1, 2 coordinate plane, that means the only contributions here are when alpha and beta are 1 and 2. So in this case, the loop can be expanded as A11 partial with respect to x1 product with partial with respect to x1 plus A12 partial x1 partial x2 and so forth plus A21 partial x2 product with partial x1 plus A22 partial with respect to x2 product partial with respect to x2. So in other words, all of the components of A where either alpha or beta are equal to 0 or 3, all of those components vanish. Now let's notice a very important feature of this tensor A. It has components A alpha beta equals the integral from 0 to 2 pi over the loop of V alpha V dot beta. Now let's integrate by parts and write this as the integral from 0 to 2 pi of partial with respect to lambda of V alpha V beta minus the integral from 0 to 2 pi d lambda V alpha dot V beta. Now this, of course, the first term is V alpha V beta evaluated between 0 and 2 pi, but as we've seen before, that's just going to be 0 because V is 0 at both lambda equals 0 and lambda equal 2 pi. So what we're left with is just this term. That's the integral from 0 to 2 pi of d lambda V beta times V dot alpha. But you'll notice what we have here is just the components A, beta, alpha of the tensor A. So what we've shown is that the components of the tensor A satisfy A alpha beta equals minus A beta alpha. So the tensor A is antisymmetric. And in terms of the expansion in a coordinate basis, of course A11 must vanish because, again, the components are antisymmetric. A22 must vanish, and A21 is equal to minus A12. So we can write the expansion of this tensor as A12 times partial with respect to x1 outer product with partial with respect to x2 minus the other way around, partial x2 partial x1. This result, of course, assumes that the loop lies in the x1, x2 plane. Whereas A being antisymmetric, this result holds for any loop. How do we interpret this component of the tensor A? Well, if we go back to our definition of A alpha beta, this can be written as integral from 0 to 2 pi of V1, V2 dot. And we know since A is antisymmetric, this is minus A21, which is minus the integral from 0 to 2 pi of V2, V1 dot. So we can use this to write A12 as 1/2 the integral from 0 to 2 pi of V1, V2 dot minus V2, V1 dot. And let me write this schematically as 1/2 sum, so instead of an integral sign I'll just use a sum of V1, V2 dot d lambda minus V2, V1 dot d lambda. If V and V dot were vectors in three-dimensional space with Cartesian coordinates, you would recognize this combination as being the 3 component or the z component of the cross product between V and V dot times d lambda. So this is the 3 component of V cross V dot d lambda. And the reason for pointing this out is because you'll recall that the magnitude of the cross product is the area of a parallelogram spanned by the 2 vectors. Let's return to the picture of the loop. So this is the base point P, and here's the loop. This is the vector V that connects the base point with the point with parameter value lambda on the loop, and I'll call this now V with a little arrow symbol over it. And this vector connects to the point lambda plus d lambda on the loop. And you'll remember this is the vector v dot times d lambda. So the cross product of these two vectors is the area of the parallelogram spanned by the two vectors. And that's just twice the area of the triangle formed by this wedge between the vector v at lambda and the vector v at lambda plus d lambda. So this combination of components is twice the area of the triangle. And the factor of 2 cancels the 1/2 here, so the A12 is the sum of the areas of the triangles. The triangles formed by the vectors, the displacement vectors v at various values of lambda. So this is just the total area of the loop. And by the way, this is not the proper area of the loop, it's the coordinate area. So if this is the loop, and these are my coordinate lines, the loop lies in the x1, x2 plane, so this is x1, x2. So the area is just counting the number of coordinate tiles within the loop. Let me summarize what we've learned about this tensor A. So A is a type 2-0 tensor. It's antisymmetric. And it defines the plane of the loop. And it also defines the size of the loop. The size, meaning the coordinate area of the loop. And by the way, in some contexts, an object like this is referred to as a bivector. Let's see if we can remember why we started talking about this tensor A in the first place. Recall we had an expression for the change in a vector u as it's parallel transported around a loop, and that expression involved this tensor A. Let me scroll up and see if we can find the result. It's right here. So this was the tensor A. So this is equal to A alpha beta. So this is our expression for the change in the vector u as it's parallel transported around the loop. So let me repeat that. We have minus partial alpha gamma mu beta nu plus gamma mu alpha sigma gamma sigma beta nu times u nu, all of this evaluated at the base point P, and then times this factor A that defines the area and the orientation of the loop. The coefficient of A in this expression has lots of indices, but you'll notice that 2 of the indices, alpha and beta, are wired together with the indices on A. And A is antisymmetric. Anytime we have a combination like that, let's see what happens. Let's refer to the coefficient as just m alpha beta. So I'm just suppressing the other indices in this expression. And it's wired together with this antisymmetric tensor A in this way. And because A is antisymmetric, we can write A alpha beta as minus A beta alpha. But both alpha and beta are repeated indices in this expression, so we can call them anything we like. In particular, we can let alpha be beta and let beta be alpha. So this is equal to minus m beta alpha a alpha beta. So now looking at this equality, we see that we can write this as m alpha beta a alpha beta is the same as 1/2 m alpha beta minus m beta alpha times a alpha beta. So when we multiply m by an antisymmetric tensor A and wire the indices together like this, then it automatically just picks out the antisymmetric part of m. In fact, the symmetric part of m is just killed by wiring it together with this antisymmetric tensor A. Now the change in the vector u as it's parallel transported around the loop can be written as minus 1/2, and I'll just take the antisymmetric part of this, partial alpha gamma mu beta nu minus partial beta gamma mu alpha nu plus gamma mu alpha sigma gamma sigma beta nu minus gamma mu beta sigma gamma sigma alpha nu. All of that times u nu and the loop tensor A. And I'm not going to bother to write evaluation at the point P here. All of these quantities are tensors at point P. A is a tensor at point P, U is at point P, delta U is at point P. And so this expression, this coefficient, is a tensor at point P, and it's called the Riemann Curvature tensor. Or sometimes we'll just say the Riemann tensor or the curvature tensor. We'll denote this as R mu nu alpha beta. And by the way, it's not difficult to prove that the Riemann tensor is in fact a tensor. We know that U, A, and delta U are tensors, so we know how they change under a coordinate transformation at point P. So you can use this expression to work out how the Riemann curvature changes under a coordinate transformation, and it changes just in the way that a type 1,3 tensor should. So let's repeat the definition here. R mu nu alpha beta is equal to partial alpha gamma mu beta nu minus partial beta gamma mu alpha nu plus gamma mu alpha sigma gamma sigma beta nu minus gamma mu beta sigma gamma sigma alpha nu. And this characterizes the curvature of the space or space-time by telling us how a vector parallel transported around a loop, an infinitesimal loop, will change. And it just changes by minus 1/2 R mu nu alpha beta U nu A alpha beta. So we can interpret the Riemann tensor as a machine, and it takes as its inputs a vector, that's the vector u, and a loop defined by this antisymmetric tensor A, and the output is a vector delta u, and that's interpreted as the change in the input vector when it is parallel transported around the loop. Let's spend the final few minutes of this lecture looking at an example. We'll take the Schwarzschild geometry. So the metric has components minus 1 minus 2m over r, 1 divided by 1 minus 2m over r squared, and r squared sine squared theta. Those are all along the diagonal. The off-diagonal terms are all 0. And from here we can compute the Christoffel symbols. gamma mu alpha beta is 1/2 g mu nu partial alpha g beta nu minus partial beta g alpha nu. That's a plus, and then minus partial nu g alpha beta. And then we can compute, knowing the Christoffel symbols, we can compute the components of the Riemann tensor. They're given by this expression right here. And of course, that's a lot of calculation. It would probably take hours to carry out all these calculations. So it's really beneficial to use a computer algebra system to do this. Let me just quote some of the results. For example, RTTT is 0. Actually, you know that must be true because we know that the Riemann tensor is antisymmetric in its final two indices. So if those two indices are the same, the tensor component must be 0. If we look at the component TR, that's equal to minus 2m divided by r squared times 2m minus r, and so forth. Let's ask a concrete question. Let's say we have a vector u, and we'll take that vector to be d by dr, and we'll take a loop at the point, say t equals 0, r equals, I don't know, big R, theta equals pi over 2, and phi equals 0. And we'll take it oriented in the r phi plane. So our tensor A alpha beta is just A r phi times d by dr tensor product with d by d phi minus d by d phi tensor product with d by dr. And this component A r phi is the coordinate area of the loop. And it should be infinitesimal. So now the change in this vector u, as we parallel transport it around this loop, is given by minus 1/2 the Riemann tensor, r mu nu alpha beta times u nu times a alpha beta. But the only non-zero component of u is the r component. So this is minus 1/2 r mu r. And the only non-zero components of A are A r phi and A phi r. So this is r mu r r phi 2 A r phi. So this simplifies to minus r mu r r phi times the coordinate area of the loop. And these components we can compute, again, using some computer algebra systems. We find RT RR phi and RR RR phi and R theta RR phi are all 0, and R phi RR phi is equal to minus m divided by 2m minus r times r squared. So the result then is that the change in u is entirely in the phi direction, and it's just given by minus this, that would be plus m over 2m minus r, and we're evaluating this at the point r equals capital R, so that's a capital R, times r squared, and all of that times the area of the loop. So if we have a vector that points in the r direction, and we parallel transport it around an infinitesimal loop in the r phi plane, it will be rotated somewhat into the phi direction due to the curvature of the Schwarzschild spacetime.